Yeah, welcome also from my side. It's my pleasure again for being here presenting from Rodian Schwarz the measurement equipment view for power electronic measurement challenges. So today we'll have a view at typical measurements and how these are affected by some parasitics and what could be done there. Of course, losses are important, stability, efficiency, and also the EMC itself. For the main challenges, we'll have these transitions to wide bandgap materials. We thus have also a wider dynamic range needed. So we are having higher voltages, but also lower sleep currents in nowadays designs. And thus the question typically is how to qualify all of them with the least amount of measurements. Also, alignment between the signals is important to get the right measurements for power and especially the losses. But typically, we are limited somehow in nowadays designs in the accessibility, and thus we'll also come back to that later on, how this affects your measurement. So not all under all circumstances you'll have something like that where you'll have a slightly huge cap already. There you could use a spring tip and a passive probe to that, but let's see which concepts could be used there. What's important to keep in mind when you're switching to a semiconductor with a faster switching inside, you'll have a wider induced spectra there, and thus you might have to consider more effects on your circuitry than ever before. So from the transistor itself, it's not only that you'll have the transistor inside, also this transistor has to be connected to the package. And in that case, it doesn't matter if you're using any other techniques like flip chip or something like that. At the end, you'll have some connection, some bolts, and these are adding a mutual inductance due to the length. And that's very important. The faster you're switching inside, the more likely you're seeing the effects of these additional parasitics of your housing. So basically, everything can be interpreted as an RLC network. And as we all might remember from our studies, we'll have an increasing effect of these parasitics with the frequency. So the faster we are switching, the higher the frequency components induced come, the higher will be the effects of these parasitics, and thus also the losses caused by these effects. So with the losses, it's not only the saturation that might occur inside a ferrite material, it's also meant for the general inductors that have other resistances and thus are causing other losses inside the systems as well as the caps. For the cabling, there we'll have the same. At the end, it all depends on line theory. So the longer the cable, the more likely we'll have transmission or dispersion effects in that way caused by the cabling. And also the pure construction of these cables. So the quality of the copper inside, the insulation between the single wires and so forth will give you different parasitics in dependency of these cables. And typically today, we recommend to use only high quality connector cables because otherwise, if they're too cheap or maybe also sometimes too old, the copper is not that clean. You'll have higher losses and you'll have a high effect on your measurement caused just by these parasitics inside the cabling itself. Not only the cables have parasitics, also the connectors itself. So we'll see different variants of the banana plugs, so with 4mm connectors here. And of course, the mechanical dimensions are somehow fixed, but in dependency how good they are manufactured, these will also have effects and differences in their connections by just exchanging some cables. And especially with these additional security connector, there's an additional cap on there. Also, the parasitics are influenced by the clips. So if we're using the crocodile pincers or other style of these pincer clips, which can draw a higher current than the smaller ones, all of these have different geometries, different lengths, and thus a huge and significant influence on your achieved measurement result. Overall, we're putting together a complex circuit which will consist of these different equivalent circuit diagrams, and thus at the end influence our desired measured step. So the ideal step is drawn blue, and most likely you'll see something like this on your screen. So you'll have additional ringing, maybe also emphasis in the overshoot, just by adding up these different resonance circuits. So if you'd like to repeat measurements and especially also to compare measurements between each other, also between different days where you do the setup, please always ensure that you're having the same quality grade cables and accessories, and also stated in your measurement reports which accessories have been used during the measurement campaign. Otherwise, it might be difficult to reproduce measurements because you are having exchanged maybe the crocodile clamps by a pincer clip, or you used a low quality cable inside your setup for the first run. For the second run, you got another set of cables, and this could already change significantly your measurement results. At the end, also the results are affected by the parasitics inside the package. So the major question always will be, if you're measuring a slow slew rate coming out of your semiconductor device, then you would expect from the data sheet of the switching device, this will be affected by the dispersion coming out of these different effects that I've just discussed. And basically, you're always adding low-pass filters by the caps. The inductances will add for the ringing, and the resistance, of course, will cause a voltage drop. And that's why it's very important to take care about all these parameters and not only to consider that there's some oxide at some position and maybe get rid of that by mechanical stress to the surface, and also to be aware of these high-frequency effects. If we now look at our high voltage differential probe, at the end, we'll have our oscilloscope, which is connected by a 50 ohm cable typically to the differential amplifier. And this differential amplifier then has its divider network front connected then to your DUT. And that's a very low frequency view. As we've just learned, we'll have to extend that a little bit by the cable, the pincers, and as well the package itself. And if we'll consider all these, this will have negative effects on the effective bandwidth. So even though the probe might have 100, 200, 400, 500 megahertz, doesn't matter, the overall circuitry defines the effective lowest frequency usable there, and this will then immediately be seen by additional ringing, changed overshoots, and of course a reduced common mode rejection ratio. So the first tip from my side would be, if you think you might have an issue with your setup, you could prove the effective common mode rejection ratio by measuring plus and minus at the same point. So having both of them clamped to source, let the device switch and have it look there on your screen how much ripple is effectively left on your oscilloscope screen, because this gives you immediately the common mode rejection ratio on screen. So you don't have to do any maths. You immediately see how large is your effective common mode rejection for this current example. Also, the colleagues did a comparison between some really cheap accessories they found in the lab and the standard delivery accessories of the RTZHD. And as can be seen, it makes a significant difference if you're using the high value products. So the white curve, you'll see less ringing, less overshoot, or the low priced accessories. And this shall just give you an indication that it's valuable to think about all of these details, because otherwise you might start hunting phantoms in your design. Because if you would assume this one is caused by your setup, you might start to be worried about the effectiveness as well as the longevity of your setup. And that's why it's very important to be aware of these high frequency effects. Also, if we're comparing different permutations, so using the ZHD cables clips with cheap clips, the high quality cables, or cheap cables with high quality clips, and so forth, you'll see you could adjust your measurement results to your needs, but they will not represent the real values. And in this scenario, you'll see a worst case 5-volt overshoot, which will mean a measurement error of about 62 to 5%. And even in best case, you're still with 12 to 5% affected for such a high slew rate. And not only the rise time is changing, also if you look at the spectrum, there's a significant difference in the spectra visible. So you'll see for the cheap cables and clips, you'll have a low pass filter added, so the higher frequency components are much more attenuated. You also see that you'll have some gain inside for the usage of cheap cables with the high quality clips. And for the high quality cables and cheap clips, you'll see also a different spectrum. And that's very important to be aware of. It's always valid bullshit in, bullshit out. So if you have a crappy cable, please consider to replace them on the long term or even on the short term through appropriate new cables from a standard vendor of these. As mentioned already, the packaging has a high impact today on what we are seeing there. So we know already these BGA, so ball grid array packages from the semiconductor devices for quite a while. So in the range of computing, system on chips, and so forth, these no longer have any footprints like a TO package or something like that. You'll always have these ball grid arrays. And if we see the development of the different packages today, so the TO, you might get some silicon carbide, gallium nitride devices in that form factor due to legacy reasons, but the more commonly used ones are no longer having these leads there, and that's due to these parasitic effects. So one would like to avoid that you're having additional inductance added to get the devices switching as fast as possible and to also avoid excessive ringing inside your system. And that's how it looks like. So for the slow inductance packages, you'll see a rectangular signal. So switching on and off looks quite nicely. If you'll have a gate resistance added to these high inductance packages, this looks also a little bit better. But if you still stay with the older packages, the faster the semiconductor gets, the more resonances you will see. And this will give you also some headache for EMC purposes, also for the heating losses and the parasitics that are occurring there. At the end, we'll have a step coming from our semiconductor. Then we'll go to the package, to the test port. And of course, at the end, we'll also have there the cabling going then to the high voltage differential probe, scope, and so forth. So all of this adds up to a distorted waveform. We'll see at the end. So we shall never forget that these dispersion effects are always to be considered. And that's very important. If you're measuring here at the outer dimensions a much slower slew rate than you would expect from your device, this might be caused by exactly these effects. And typical rule of thumb is that even from the fast switching devices, you'll see at the outer testing points not more than about 100 to 200 megahertz of significant energy inside the signals. That's all due to this low pass behavior of the connections in between. So even if we are using new packaging technologies, we still have the point of this limited accessibility. So we are unable to connect directly at the outer pins of these devices. Also current measurements will have to use maybe a shunt resistor, or we'll need some structure which we could use as a coupling port. We'll have these connectors, even if they're MMCX. Those are quite bulky in comparison to these little, small, tiny semiconductor devices. And that's why measuring these signals clearly and having a good match to the initial expected values becomes more tough. Just when you're also thinking, okay, if you have not considered to have a test port or test point here on the board, if you're adding these connectors via a short wire to the testing points, Please always keep in mind that each millimeter of these wires will give you an additional 1 nanohenry of inductance into your system. So worst case, you're adding so much inductance, so much load, that these circuits are becoming resonant, and then you might destroy even your semiconductor by just adding the test point. So far, so good for the voltages. Let's jump to the currents. I guess you're all familiar with these type of current clamps, more or less famous thanks to Hiyuki current probes there. And for these, if you look in the data sheet, you'll have a certain bandwidth, sensitivity, maximum current, but you're limited in the accessibility. So you'll have to ensure that you'll have a structure where you could clamp this huge and bulky thing about. So in addition, you'll have saturation effects occurring. So you'll have a ferrite in so the ferrite inside the current clamp gives you a translation of the flux and the possibility to measure the current on the primary winding, which will be the DUT, fed to the secondary winding, going through the circuitry, then down to the connection to the oscilloscope. And we'll have a look on the concept of the insertion impedance and the positioning effects of these current probes. Basically, in easiest case, a current probe is a transformer. As mentioned, we'll have a primary winding, we'll have a secondary winding, maybe several secondary windings around this ferrite core, and then we'll get somehow a resistance that we are inserting into our DUT. And if you'll think about these transformer equations, we'll see that the introduced inductance, or more generic, the introduced impedance to the system is somehow translated with the number of windings in that way. And that's very important to keep in mind. So if you'll have a measurement equipment coming with about 50 ohms on that side, having a requirement to have a maximum of 1 ohm load on this primary winding, you'll need at least a 1/7 transmission ratio. And if you'll have higher impedances, then this transmission ratio has to be even higher. When thinking about these equations a little bit further, we also see that there's this arrow on these probes. So first thing for these probes is, as we can open and close them, that you ensure that they stay closed at the top, so that you really push this one to the end. Otherwise, there will be a small gap. So this gap would be then reducing the effectiveness of the ferrite, and thus all these calibrations that have been made would no longer be valid. And also the losses would be increased just by the ineffectiveness of the ferrite inside. If we now look for the position, so if we have a small wire going through this one, it could be easily in one of these corner cases and every permutation in between. And if you'll see, high frequency effects can already be observed starting at about 200, 300 kilohertz. So if you think about today's switching topologies, where you have easily about 2, 3, 4 megahertz of switching frequency, if you'd like to, it strongly depends on your position, how your measurement is affected at the end. And that's very important to keep in mind. If you'll have the chance to get a certain adapter in between to fix the position, this will significantly improve the reproducibility of your measurement. Also, if you'll think about using a Rogowski probe, typically these are thought to be independent of how they're oriented to the DUT. That's more or less right. If you only consider the inner conductor here, as soon as you start to consider the coupling to the outer world, you'll see that this one is also strongly depending on the orientation to the DUT, to the heatsink, and so forth. So also please be aware for the Rogowski coils, these are highly resonant structures. So yes, we have a weak coupling between the DUT and the measurement system itself, but we are having a long wire in between, which is then taking a lot of turns inside with Rogowski coil. Also inside, there's a feedback loop to ensure that the loop is closed. And thus, these systems are highly resonant and also highly depending to its resonant environment by the cross-coupling effects. And as you can see here, you'll see different readings in terms of the current. You'll see different overshoots, ringings, modulations on that. So it strongly depends on the position. Going back to the traditionally used current probes using a ferrite core inside, if you look in the data sheets, you'll find these saturation curves. And please ensure that you're not exceeding these values. And that's quite important to be aware of. We'll have a derating over frequency because the losses of the ferrites will increase over frequency, and thus these probes will heat up. And in a worst case scenario, I've seen that already several times, the current probe will melt down because they got an excessive amount of current seen on the primary side, which caused too many losses. And then you'll have to tell your boss why you need another current probe. So please be aware of these derating curves and check upfront what frequency range will most likely be induced by checking for the maximum slew rates as well as the switching frequencies inside your system. If you'll further make a deep dive into the construction of these and why there's this arrow on top. So basically, a current probe will be looking like this. So primary winding, secondary winding will have termination. But all the probes on the market are not starting for a certain AC value. If you'll take these from Hioki, for example, or also from R&S, these are AC/DC zero flux probes with Hall elements. So what does this already state in the name? We'll have a Hall element to measure the DC, and this one then goes to an amplifier to inject there the inverse flux to avoid saturation effects to the core. And due to that, it's important to know in which direction the current is flowing, because otherwise the circuitry is not able to compensate for the DC flux and also the low frequency flux deviations there. For Rogowski, I already mentioned the base construction. We'll have the integrator circuit at the bottom. Then we'll have these different high amount of windings, which is a soft coupling because we have no longer a ferrite core, which then translates the flux of the current to the orientation of our probe itself. And yeah, in the middle, we'll have this line back. And as you could assume, this one could easily go in the range of several 10 centimeters or even meters of cable inside the probe. And thus the usable effective bandwidth is limited by the integrator and the amount of cable upfront. Last but not least, the shunt resistor. These ones are quite convenient because they will offer you the highest possible bandwidth and also the most discrete system for AC as well as DC, because you could do calibrations upfront on these resistors. Nevertheless, when using a shunt resistor, please always keep in mind if you would like to do efficiency measurements, you always have to choose between the measurement of the right current or the right voltage. So in that way, you'll have to split up your efficiency measurements to at least two measurements. One where you're measuring just the current of the system, and the second one where you're measuring behind the resistor or even without the shunt resistor to get the right losses of your system. Otherwise, the dissipation of the resistor itself plus the probe would give you a wrong reading, and thus you would say you'll have higher losses of your system due to not having accounted these losses correctly. So summing that up, we have different types of current probes. The standard current transformer, the zero flux, plus the compensated flux sensors. We have Rogowski coils, we have shunt resistors. And as you can see, each of these methods has the pros and cons. Basically, for these standard current transformers, they could be constructed for kiloamperes inside, but you'll have to ensure you'll have a test position also for these others where you'll use clamps. They are quite intrusive, so you'll always have to add a certain amount of wire for being able to connect the probe, or you'll have to use the connection cables to your inverter. In terms of bandwidth, they are also somehow okay or limited, strongly depending on the type. Um, and there, in terms of bandwidth, the shunt resistor is typically outperforming each of the other systems, but still you'll have to make sure you'll have a certain test point considered for these shunt resistors for being able to add them. Otherwise, you'll have also to separate your lines to get that one in. At the end, there is no perfect solution right now on the market. There's a lot of research going on to find some new systems, like, for example, these infinity loops and so forth. But there's no standard solution right now, and you'll have to be aware of all these pros and cons to decide which of these systems gives me the most insights into my system itself, and how to consider that for the measurements of efficiency and so forth, that you're not doing the right calculations of voltage multiplied with current, so that you might have to do that into separate measurements and afterwards align them. This brings me already to the end of my part of the presentation today, and I'll be happy to answer your questions.
All right, thank you very, very much. So as I think we've mentioned before, you can mouse over the QA icon on the bottom of your Zoom webinar interface, and you are able to type in questions right there. The number one we always get is the presentation going to be available? And yes, it will be available. We will send them out via email in the next couple of days, or you can always go to monolithicpower.com/webinars and be able to find them all there. All right, but let's jump into some of the questions we have gotten. Would there be improvement using the LVDS interfacing in send signal to a receiver?
This could be one solution to avoid some of these artificial cabling effects, but at the end, then you would have to build in the high quality ADCs there. You would have to ensure the stability in terms of grounding. So it's just a shift of drawbacks in that way. And it's more easy to construct these transmission lines and consider the accessories there for a high quality, to ensure that your measurement system is not affecting the measurement too much. So there, I would always say, in general, yes, it's possible to make that with a remote head sample or with a remote sampling head, but the drawbacks will be very significant. So I'm not sure if this would be the best benefit.
Great, thank you. Next up, we had, how would you perform a measurement of drain source and gate source voltage of a high side MOSFET? And then goes on to say, I soldered directly on a MOSFET drain source and gate source pins, twisted cables, and then connected to my differential probe. And I'm seeing some weird effects on my gate source signal, maybe due to some parasitic effect.
Mm-hmm. Yes, so that's a slide I did not have in the slide deck today. But if you're twisting or not twisting the cabling, changes heavily the capacitive or inductive loading of your system. So if you're twisting them, you're increasing the inductance. If you're leaving them untwisted, you'll have a higher capacitance. So as generic rule of thumb, the only thing that helps to press down resonances overall is to shorten the cables to a certain minimum. And that's the only recommendation I can give here, to go for as short as possible connection. And then also consider the input impedances of the probe. So if you might have another active probe that could be used with a lower input capacitance, this might also solve some issue here. So it's very important that you'll keep the cabling as short as possible. The idea of soldering as close as possible to the drain source or gate source is good, but yeah, somehow limited and strongly depending on the package size. So in this case, you're lucky that you have the chance to get some soldering there.
Okay, next we had adding a small RF connector to the board as a test point might be helpful. I guess maybe a comment more than a question, but if you have something to address there.
Yes, so basically from a testing point, this would be helpful. On the other hand, if you leave an open connector in your system later on, this would be additional costs to the design per piece. If you remove that one later on, you might have a change in the parasitics of your PCB, and this might cause a different behavior. So typically, we have the recommendation right now to have two designs. So the first one, which is specifically for test purposes, where you will have this dedicated test points in, and the second one will be later on used for the production, where you do a last verification with some soldering made, where you'll have the connectors added by a small wire there. But at the end, if you'll have open structures, then you always have a chance for EMI issues inside the system. So even if it is small, these disturbances might cause another coupling path by providing other geometries. So that's why it's a pros and cons, and has to be considered. If this connector could stay in, and you might add another cap on that to ensure also isolation, then this could be done. But at the end, you'll have to judge if this could stay in the complete product. Otherwise, you might have changes in the system behavior afterwards due to getting that connector out and maybe also changing the complete PCB. And then all the measurements you made with the connector would be more or less just guessing how it behaves with the initial design of the product, real product.
Okay. Can input bulk decoupling and low pass filtering be done simply with bulk ceramic capacitance? For example, two 100 UF 1260 capacitors.
Um,
1206.
Basically, there I'm not the hardware engineer. Of course, adding low passes can help to suppress, but on the other hand, from a test equipment perspective, I'd like to qualify the system like it is. So typically, that question has to be answered from the view of the outer world. So if you'll have to ensure that your switch mode power supply at the end is not too sensitive for some burst surge events or to high frequency coupling inside the system, that's a different story. When you're talking about the test points, if you're adding caps there, you're adding an AC coupling. So then you would only be able to measure the frequency components with some attenuation over the cap itself with the measurement system. And so at the end, I would not recommend to do so, to add dedicated test caps in that way. The probe shall be chosen that is able to handle these offset voltages. And there are also optical isolated probes available, which also deliver a very high common mode rejection and isolation if this is needed for analysis on highly isolated switch mode power supplies. So generic answer, no, I would not make dedicated test points using caps. If there are some that could be reused, that's good. But everything for these low pass filters and so forth, as the connections to the outer world, that's part of the design of the switch mode power supply, not for the measurement equipment.
Next up, we have, do you think the shunt can't achieve a precision that's the same as a flux gate? Many shunts prove very low TCR.
That's strongly depending on which type of shunt. There are many manufacturers around, and the flux gates are also somehow limited in terms of usability. So, as mentioned, there is no good solution available currently, and that's why you will have to decide for the solution with the least drawbacks for your measurement task. That's the only recommendation I can give here.
Thank you. I think going back to the prior question about twisting, and they're making twisting cables increase capacitance and reduce mutual inductance. So,
if I phrased it the other way around, I would be sorry, but I could add the slides for the handout so that there this information is added. Then
right.
we'll have the correct right thing and not having me bust up something.
All right, so and just to be clear here, we're going to send out all the presentations in the next couple of days, and so we'll make sure that we get it added there and address your question that way. Next up, how would you rate coax cables compared to twisted versus non-twisted wires for these types of measurements?
So this again depends on the voltage rating. So if we are talking about 1, 2, 3, 4, 5 volts, the coaxial cable would at least not have an isolation issue. If we're talking about 100, 300, 400, 500 volts, these cables would need to have a certain isolation distance and thus get very bulky, unflexible, and yeah, more or less unusable in that way. Second thing to be aware of is if you'll have a coaxial cable with a certain geometry, this could add a lot more of capacitance to your design than using the twisted pair lines. So here again, it all depends on the voltage levels, and there's not a true yes or no. So it's not always the best solution to use a coaxial cable, and it's not always the best solution to use twisted pair banana plugs. So it's all up to the system behavior at the end. But the higher the voltage gets, the more important is the question, do we really have to see the full offset voltage? So if we're measuring over a shunt, we'll just have the delta when using an isolated probe. If you are using a high voltage differential probe, we always see the complete voltage difference, including the offset voltage. And there, the coaxial cable would see a voltage difference, including the offset too. So there, the cable would no longer be appropriate in that way.
Thank you. What kind of test points do you suggest?
Oh, that's a tricky one. So the test points, as mentioned, could be pads, could be caps, could be soldering points where you'll have the connection of your semiconductor itself. The more important thing is that you'll know for certain test points that they are somehow aligned between each other so that the time difference is the same for the traveling of your incident steps there. And if you're going far away from your semiconductor with your test point, this would have the drawback that you'll have a lot of inductance in between again and capacitance, depending on which frequency range we are talking there. And due to that, you would see the dispersion effects of your signal traveling from the semiconductor to your test point. So these shall be as close as possible at your device under test. Otherwise, you'll have to ensure, and this doesn't matter if you do characterizations using a VNA or using a simulation to get these, you'll have to be sure that your system is not affected or corrupted by the definition of these test points. And that's most important here.
Great, thank you. Not sure how to. Not sure what that word is. How to for measurement of voltage or current in a double pulse test.
Um, yeah, so here again, first of all, the target for the design of this double pulse measurement shall be for having reproducibility and also accuracy achieved inside the system. So this is more or less related to the test point question from my perspective here. If we have a double pulse tester where we use a generic coupling plane, there typically we'll have some defined test points for current as well as the voltages applied to the DUT. And then we are able to plug and unplug the DUT there by some robots and push them into the connectors. So here again, the major story will be you'll have to ensure that you'll know your boundary conditions in that way, and then you could do what you'd like to do in this meaning. So for the double pulse test itself, there is no specific need to have a dedicated, highly sophisticated probing fixture, as long as you know how your voltage and current are related to each other in the timing perspective. You could do all the calculations for the energy losses as well as the correlations of your signals by looking for the Miller plateau and thus correlating it with the current and voltage then also. So also the efforts for calibration are quite different in dependency of how you do the tests and how the characteristic behaviors inside your traces are visible. If you see a lot of ringing inside your signal, typically you cannot do any correlations. If you'll have a nicely shaped curve, then you could do these alignments easily afterwards in the post-processing.
Great, thank you. Next one was, what about no contact testing like an antenna? Isn't that the real test? How is this product going to affect the 1 and the 100 megahertz receiver nearby listening to a broadcast radio?
So that's a yes and a no. If we're using antennas, these antennas are tied to a certain physical principle. So if we're using dipoles, those are mainly tied to having a traveling wave with a so the electrical field perpendicular to the magnetic field there. If we're using a magnetic field probe, so a magnetic loop antenna or a near field probe constructed in that way, these are relying on an AC current flowing initially on the DUT. And we'll have to differentiate here two things. So the aspect brought up here is investigating the electromagnetic compatibility of the devices, and here also only the electromagnetic interference testing, so that we are ensuring that no radiation is taking place that could be harmful for the surrounding. The previous things I've been talking about mainly in the presentation were about doing efficiency measurements, doing the qualification of the base function of the switch mode power supply. And there, in a first step, I don't care a damn about EMI in that way, because I'd like to ensure that this thing is switching first of all, providing output power by a certain input power. Second step would be to ensure that I'm not feeding too much high frequency components to the input, not getting them at the output. So everything that is cable bound emissions there. And last step will then be to investigate, okay, how much of these high frequency energy that I'm generating by switching between 1 and 0, so high and low potential, is radiated to the environment, and do I have to take care about that? And then you'll have to hunt down, is this caused by direct radiation out of the package, or is this caused by the harness in the surrounding? And these are many different steps. So yes, it is one test to use antennas. This would be typically pre-compliance tests using near field probes or going to an EMC lab in an anechoic chamber to see what's going on there. But then you would completely ignore that you also have the physical contacts, the harness, the grid connections, and so forth. These have also to be tested on top. So the system itself has to be ensured to meet all these regulatory affairs there. And therefore, you'll have to take care about the conducted as well as radiated emissions. But upfront, first of all, you'll have to ensure that this thing is doing what it's intended to do before you'll take care about the unintended things like in the EMI.
Great, thank you. For WBG power devices such as GAN, would you recommend the usage of a Rogowski coil for the drain current measurement?
So this heavily depends on your needs. As shown in the presentation, these Rogowski coils are somehow resonant structures. They are depending on their cross coupling for these higher frequencies. But also, if you remember the beginning, we'll have anyhow low pass filters up front. So it's kind of unlikely that you'll have a propagation of your maybe let's say 1 picosecond step inside your switching device coming out of that package via the bond wires and so forth, because the inductors added by the chip connections or package connections inside, as well as the outer world, will always act as a low pass. And the experience says that we are not expecting significantly more than 100 megahertz of frequency components. If you're lucky, having very tiny structures and so forth, maybe 200. But that will be the real high end of the cable bound emissions, even for SiC and GaN. I have not seen something much faster yet. It changes the smaller the geometries get. So if we're talking about testing of switch mode power supplies integrated into a SoC or into a CPU using wafer needles and so forth, that's a complete different story. But I guess that's not the question that was targeting to.
Great. Let's see. How would you measure voltage ringing on a SW pin of sync buck converter that converts HV, e.g. 400 volts down to 48 volts? What kind of probe would you use?
So basically for 480 volts, of course, a high voltage differential probe could be used to do that on the input side. On the output side, a standard differential probe with an additional 10 by 1 attenuator could be used to to get the signals out. And I would make a split between these two probes due to the way lower capacitance of the high-speed differential probe. So a standard differential probe you would typically use to probe a CAN, LIN signal there. So any differential signal that matches to the bandwidth. And I would use the other probe due to the high input voltage needs there. So this always depends on which test point you'd like to define. If you're going for the high side gate and also the 480 volts to mid voltage, then of course a high voltage differential probe is needed. If you'll have an isolated supply design, then the question would be if the common mode rejection of a standard differential probe is sufficient or not. And that's a second part of the story. So there an optical isolated probe could be used, but this strongly depends on the isolation against ground. So there, I would always use an active probe as first statement, and of course choose the appropriate probe to the input voltage levels there.
Great, thanks, Alex. That was the last of our questions. I do see a couple of people had raised their hands. If you do have an actual question, look for the Q&A button at the bottom of your Zoom webinar interface. Click on that and you should be able to just type it in. I see that we do have, no, that's the one we just did. So we do have about 9 minutes before we start our next presentation. So if there was anything else that you wanted to ask, please go ahead and fire away. So we got a comment thanking for the webinar. You're very welcome. Remember everyone that these will be available on demand. So we will send you out an email in the next couple days. It takes us a little bit of time to process the video, but then we send that out to everyone, or you can always go to monolithicpower.com/webinars, and from there, be able to see all the old ones that we've done. And there's been quite a few on EMI. So if you want to look back through some of the old ones, just take a scroll there.